haven't gone over, but it's a very important concept to understand. And that's DC power supply. So what advantage does DC have over AC?
DC would be smaller wires.
Well, the gauge of wires has nothing to do with it's AC or DC. The gauge of wires depends on how much power you're transmitting at a certain voltage, right? You understand? So we buy and sell power because power is work, right? Understand that? And of course, the way we calculate power is equal to V times I, right? You understand that? So how much power we need to transmit? So conductors are not rated in voltage. What are they rated in? Huh? We only got three things, guys. We got voltage, current, and resistance. What's conductors rated? You can't have yeah, but that's not what they're rated at. It's called ampacity. How much current can that chunk of wire handle, right? And voltage is a relative term. The conductor has nothing to do with the amount of voltage. That's what the insulator's in there for, to keep that voltage from pushing that current where it's not supposed to go, right? You understand? So the insulator is rated at a voltage. The conductor is rated at a current. The problem is there's no such thing as a conductor that has zero resistance. So the main purpose of the conductor is to get the power from the power supply to the what? To the load. And it does that through current, right? You understand that? So if I was to come over here, I say, okay, voltage equals to, or power is equal to V times I. Is that AC or DC? Is that AC or DC current? Yeah, it's either one, right? You understand that? The trick is I is equal to P over V. So the problem is if my wires, so we draw wires like this, but in reality, wires are this. Except they got a really, really small resistance, right? You understand that? What determines the resistance of a conductor? No, you're talking about how we induce it. I'm talking about resistance, right? What determines the resistance of a conductor? Well, the size. Okay, good. So size. No, you're talking about transformers. We're talking about resistance of a wire. Oh, the length. Yeah, that's one. Material. Yeah, let's go. And then Jackson brought it. And then 4 would be the temperature of water. So metals when they heat up. So the two main materials, of course, we use is copper and aluminum, right? Now, what advantage does aluminum have over copper? A lot cheaper, right? And a lot doesn't weigh as much, but it has a higher resistance. Aluminum is almost a semiconductor. So copper's got one electron in the valence shell. Aluminum's got 3. A semiconductor has 4, anything above 4. So aluminum has quite a bit of resistance, right? You understand? But the major thing is I'm trying to send current through a resistor, and every wire has a resistance. So Alabama Power calls it line loss. This is how much power or voltage they lose in what? In the line itself. So this is the main thing, guys. I is equal to P over V. So the higher I can make that voltage to transmit a certain amount of power, the lower the current is trying to get it there. So what does Alabama Power and TVA do when they transmit their power? They step it up to a really high voltage, right? You understand? Because what happens? They're not trying to sell current. They're not trying to sell voltage. They're trying to sell what? Power. So the higher the voltage they transmit that power at, the lower the current, which means now instead of using copper, I can go to aluminum for my high tension lines, right? But you're talking 200,000 or 300,000 volts over there. Some of your interstate lines, like the one running from Tennessee Valley down to Bessemer, Bessemer is powered up off of TVA. Bessemer is not Alabama Power. It's always done that. They used to have a big steel mill here that used quite a bit of power, and they signed an agreement with TVA to power it for them, and they ran the conductors down here, and now that's where Bessemer gets our power. So we don't pay our power bill at Alabama Power. We have to go down here to Bessemer Utilities and pay ours because that Bessemer Utilities collects that for us. But coming from Tennessee Valley down to here, they're doing about 750,000 volts. So 750,000 volts a push, they could send 750,000 watts of power with 1 amp of current. And then they send it over 3 wires, and so that would be divided by the square root of 3. So 3 phases, more efficiency. So DC, I could have my battery out there as a DC supply, and that sucker's probably got 200 or 300 cranking amps available to us. But look at the gauge wire you have running from your what? From your battery down to your starter. The wires running into your cockpit is not near as that big because they don't have to. So the big current puller in a car is that dang starter out there, and that's where the what? That's where the big wires are. Why do they have to be so big? Because the voltage is so low, right? You understand that? If we could have those batteries running it, so golf carts don't run off of 12 volts, they run off 24, which means now they can use what in there? Going back to their electric motors, they can use smaller gauge wire. Most electric cars run off like 600 volts. Why? So they can use smaller gauge wire. We could get as much horsepower out of a smaller motor, right? But it would require what? A lot more current to get that out. So the advantage of DC is that this is the advantage of DC right here. I can electronically control it. AC is real hard to electronically control. We can step it up with transformers, but that's not electronics, and we can step it down. But electronically controls it means I can take DC and I can generate AC if I want to. So you can buy a thing for your car called an inverter that you hook up to your battery, by George, and you get 120 volts AC out of that because it's done what? It's done electronically, right? You understand that? So the advantage of DC over AC. So all your electronic devices run off what? DC, whether you plug them into Alabama Power or not. They run off DC, right? There's something called a power supply that does what for us? Converts our AC over to a manageable DC, right? You understand? And then here we start stepping it down. So our PLCs over there, they're electronic devices. They operate off of what? DC. So they have a power supply either built into them or they got a separate power supply that converts the AC into DC to run the system. So the Amatro lines, you can see that real easy. The Festo lines, you'd have to go behind them. The power supply for the Festo lines is in little cubby-os behind them. So power supplies. So that's what's on the test. It's got a power supply on there. So we got 2 types of power supplies. We have what we call a linear power supply. Which is very inefficient, but it's easy to design. It's easy to fix when they break. So I just went on to Google and typed in, or typed in linear power supply, and this is what it showed me. Now this is what we call a fixed power supply. The trainer's got a variable power supply. So I can show y'all the schematics on the trainer that y'all use, this black trainer that y'all have, and you'll see this is almost the same thing. So what we have is this guy right here. This is what we call a rectifier. This guy converts AC into what we call pulsating DC. So what we do is we take an AC waveform. Let me bring up PowerPoint. Which is this, right? So this is AC. And then using these diodes, we take this and convert it into what we call pulsating DC. So a diode, and we talked about a little bit about this, a diode only lets current flow in one direction, right? Everybody understand that? Okay. So this is in your, these guys are in your alternator on your car. So your alternator says it puts out AC, right? But your car runs off of DC. So it's got to do what? It's got to convert it over to AC, from AC to DC. Okay. So anytime to forward bias these things or make them work, so these are check valves. I don't know what a check valve is. Have you ever heard that before? You're going to run into them. We use them in fluid power. We use them in electronics. A check valve is a device that only lets something flow in one direction and it blocks it in the other direction. So hopefully you got it. Most houses has a check valve on it, because if you didn't, if they turned the water off, all the water would drain out of your house. And then when they turn the water back on, it would come back on, and your meter would charge you twice, right, for the same water. So there's a check valve on there. So as long as the pressure comes in on the bottom, it opens the check valve up, and when it comes the other way, it does what? And then we looked at these check valves right here. So that's a check valve. That's the symbol of a check valve. So what happens is when the fluid flows this way, the valve opens up, right? And you can see these things. But if it tries to flow this way, then the ball seat's inside the V and it blocks it. So that's on our directional control valves. Not our directional control, our flow control. So it allows us to meter the exhaust instead of meeting the pressure. So this AC, so let's look at this AC alternation. Well, this is going to be a plus here. This will be a minus here. This guy right here is going to be off. Well, I'm sorry. So which ones are going to turn on? Not this one, because this is a what? Plus, I'm sorry, it is going to turn on. This is going to be a minus. Okay? So the current would flow out this one. It's going to go this way, right? You understand? And then it's going to go through, I'm going to put a resistor up here. It'll go through the load, and then it'll come back. It's looking for its positive, and it'll go down that leg right there. So what we did is we just passed the what? The positive alternation, so my DC would do this. That makes sense? Yes or no? Sort of. Now if we change the polarities, so current flowed this direction right here, right? So that would make this DC, that would make this side of this resistor negative, because we're seeing in the negative. This would make it positive. So what I'll do now is I'll come up here and reverse the polarity for the next alternation. So now this right here is positive and this right here is negative, right? So that means this guy is going to come up. This current now is going to, this is negative bridge. It's going to go out this one. This one is blocked. It's going to come over here. It's going to go in the same direction. It's going to come over here, and then it's going to go back to its positive. So what we did, notice it's in the what? It's in the same direction. So what we just did is we just flipped that negative alternation up to the top. But what these things give us is they give us this guy right here. We call it pulsating DC. Now, motors would like this. Light bulbs don't care for it, but electronics would hate it. So what we'll do is we'll come over here and put a device that has the ability to charge. We call it a capacitor. And what it does is it charges up on the positive peak, and then it discharges. So what we do is we'd end up with something that looked like this. So that would be what we call DC. So if we look at the print, so this is converting it to AC. Here's our filter right there. So what it does is it converts my AC into what we call unregulated DC. And then this is just a pre-filter for the regulator. This is a 5-volt regulator, positive 5-volt regulator. 7805. So what we do is over here, on this side, so over here we're getting this garbage right here. And motors love this, they wouldn't care about it. But it's going to be DC. And then on this other side, what we get, so I'm going to run this through a regulator. What a regulator does, well, it regulates this. So this is what you got on your car. And over here, this might be 8 volts. Over this is going to be 5 volts, but it's going to be a nice clean 5 volts. This would be the makeup of a linear power supply. Now, if I come up here and make this variable, which is what the trainer's got on it, then I can take this unregulated. We'll never ever get here, so you're going to have to regulate down in here somewhere. But now we'll have the ability to adjust it. So this is what the trainer has on. Now what they've added on this circuit is they've added what we call a crowbar circuit. So what are we trying to do? Well, we're trying to protect the load. We're not necessarily trying to connect the power supply. We're trying to protect the load, right? That's where your money's at. So that's what this circuit is right here. So this is a diode, what we call a Zener diode, that breaks down at a certain voltage. So if this regulator goes bad and this output goes up higher than 5 volts, then that's going to come over here. That's going to fire this guy right here. It's going to short out the power supply. And what is it going to do? It's going to blow the fuse. So this is a little different. So that's the part. So we got the transformer. What does the transformer do for us? Nobody know what transformers do? Step what up or down? Voltage or current. If it steps the voltage down, then the current's got to go up to produce that power, right? You understand? So what the transformer does, guys, it actually sets this output voltage. We don't want this regular. I wouldn't want 50 volts right there because this guy would be dropping the difference between 50 volts and 5 volts. That's a 1 amp regulator. That's 45 volts. So it'd be sitting there eating up 45 watts worth of power. So that transformer, so this guy right here is probably like a 6.3 volt transformer. So, but it's actually setting the output voltage. Now, what advantage does low voltage have over high voltage? Well, it's easier to control, but the problem is if I'm trying to deliver a lot of power, it's going to take a lot of current, right? You understand that? So what's this guy right here? Here's Alabama Power on this side. This computer has, if I plug this sucker in Alabama, right, it's a regulated power supply, which means even though I come over here and my loads are constantly varying over here in my computer, right? You understand? So when my hard drive comes up and starts seeking, it pulls more current. When I'm using my USB, it pulls more current. I got a 5 amp USB port on this thing. So instead of getting 100 milliamps worth these other ports saw, this guy right here has the ability to provide 5 amps. So if I plug something in here, 5 amps, my power supply would try to drop down, but the regulator keeps it what? It's like your car. So your car's got the same thing in there. It's got a regulator. So if the output of your alternator tries to go down, the regulator makes it do what? It makes it stay up. Yeah. So you can turn your lights on, you can run your air conditioner, you can do everything. And if you went out there and measured the output of your alternator, it's going to stay around 14 volts, no matter how many loads you're running. It will drop down a little bit because there's no such thing as a perfect regulator. So the transformer sets the voltage on output. This converts AC into pulsating DC. This guy right here filters it, right? Understand? And that regulates. And then the lab don't have this crowbar circuit. Some power supplies have crowbar circuits in them. So if you try to, instead of burning up your computer, it'll just kick out your power supply. So yeah, sometimes these guys just go, they'll kick out because if they let too much voltage get through, right, then your computer would try to pull too much current, right? You understand, because loads are designed around a certain voltage. So I guarantee you this guy here's got some type of protection circuit. But this is not a linear power supply. This is what we call a switching power supply. The problem we have with these guys is this guy right here. We transmit 60 cycles. So this guy right here is trying to maintain the load from between here and here, which would be 8.33333333 milliseconds, or 8.3 milliseconds. Because that's the time between the pulses on that's the time between the pulses. So the more I load it, what would happen is that the more load you put on there, the steeper that would be down. This is like on a battery. The more load you put on the battery, the faster it does what? It discharges. And the voltage would drop down real fast, right? So what we would like to do is come up here, and of course Alabama Power is at 60 cycles per second. We've already talked about that, right? Yes? No? 60 cycles per second, right? So that means the frequency, the time for one input cycle would be 1/60th of a second, which would be 16.7 milliseconds. So from here to here is 16.7 milliseconds. But what I've done is when I switch this up, down here, this is a cycle. So when we rectify this, I get two cycles of DC for whatever one cycle of AC. So that's why between here and here, it would be 8.3 milliseconds, which is nice to know. So if I can get the frequency up, and then I can rectify it, then that means my filter would have to carry the load for a short amount of time. So this is where they came out with. What can we do with DC? What advantage does DC have over AC? We can electronically control it. So that means if I can bring in the AC right off the bat and convert it into DC, then I can re-oscillate it at whatever frequency I want it to be at. And that's what a power supply called a switching power supply does. So it brings it in, oscillates it right off the bat. With switching power supplies, or you just can't hardly fix them when they break. These guys right here, switch mode power supplies, I call it. So this is what this is right here, switch mode power. So if it's more efficient, how much energy we transfer would be. So normally, while on switch mode power supply, they bring the 120 volts in and convert it over right off the bat, and then they'll re-oscillate it and run it through a transformer. Well, now the transformers can be a lot smaller because how much you transfer depends on the speed of the motion, right? You understand that? So what we can do with switch mode power supplies. So let's do a block diagram instead. So no transformer. What does it do? Rectifiers and filters, right? You understand that? Then it runs it through the transformer. Once it's been converted back to AC, it runs it through a transformer. But it's at a lot higher frequency. And then they go through the rectifier and filter, and then they feed back to determine the speed of the oscillator. So what we end up with, whether you understand this or not, switch mode power supplies are a lot more efficient and they are a lot smaller because the filters can be a lot smaller because they don't have to maintain the load. The problem is you can't fix them. So just about all your switch mode power supplies are going to be sealed in a block. this guy right here goes out, you're gonna do what? You gotta buy a new one. But look, you know, you got these little old, we call them bricks. Those are switch mode power supplies. Look how small those things are. And look at them real close and see how much current those things put out for that size. You know, most of them put out over half an amp for that. This guy right here, it's rated at, and the problem is that we can control this. So what we can do is we can control how much we get out of this thing. So this guy right here, with my inverter, I can run this thing on anything between, on an input voltage between, as soon as I find it, 240 volts so I can run this thing anywhere up to 240 volts, 50 or 60 cycles. It's going to take 1.8 amps of power, and I can get 20 volts out of this thing at 3.25 amps. 3 1/4 amps. Look at the size of it. So this inverter right here it's looking for a certain output. So it's going to change itself depending on to keep the output. So that means we have a wide range of voltages we can put into this thing, right? You understand? A linear power supply is going to either be designed around 120 volts or 240 volts. This guy right here, when I was in Germany, I just bought an adapter and plugged this into the wall because they used a weird plug over there. They use a round plug. Yeah, their wall outlets look like their wall outlets are round, and yeah, they're like this. They're actually round. So, but you can buy these little adapters, plug it in. So yeah, that's what's nice about it. Nice about these. What's that?
All of our stuff is shipped from Germany.
Well, they convert it over when it comes over here. So all you'd have to really do is just change the plug on it, right? And if you look, you ought to look at some of the international plugs. So of course we have ours are what? Yeah, they're 3-prong. One of them's smaller, one of them's bigger. But 240, I don't know if you ever looked at 240. 240 is all over the place. 120 is pretty standardized. Of course, this would be the common or the neutral, right? And this would be what they call the hot. And then we have the ground. And then we have this guy right here. Oops, sorry. This is also bigger. This is a 20 amp plug. And this right here is a 15 amp plug. If you look at all the plugs in this classroom, you'll see it's got the little notch. So a 20 amp device should have this T coming off of it, but a 15 amp, so I can run a 15 amp device in a 20 amp plug, but I can't run a 20 amp device in a 15 amp plug, because the 20 amp device is going to have this thing right here, right? So its neutral will look like that. So these are standard NEMA, National Electrical Manufacturers Association. And they're 15. I'm sorry. So y'all can see this at Lowe's, by the way, if you ever go by this. So the actual plug is a NEMA 15 P, which would be the plug, and it would plug into a NEMA 15 R, which would be the receptacle. And the other one is going to be a what? It's going to be a NEMA 20 P. So this is the 20 amp plug, and then of course the receptacle will be a NEMA 20 R. So they finally standardized these things for when they first started running the power grid, and how did they come up with a plug and cord on these things? Everybody was doing their own thing. So eventually they standardized the plugs. So now the whole U.S. uses what? Now, when you get to your 240 plug, so normally when you buy a dryer, it doesn't come with a power cord. Why? Because they don't know which 20 amp standard you're using. So if you're going to go buy like a dryer or something like that, or an electric water heater, you need to go out. Well, electric water heaters are usually hardwired, but your dryer's not. You need to look at the plug in your wall before you go buy the cord that goes along with it, right? Or if you're replacing it, you need to cut them off. Okay, so we're going to have a what? We're going to have a transformer. It's a linear power supply in the test. And then we're going to have a rectifier. Then we have what we call a filter. And then we're going to have a regulator. And this will be the output. So we had an instructor here that one of the power supplies went out in one of the trainers. He got a permanent marker and wrote bad on it. You know why that's funny, right? Because I can fix anything in that trainer, yeah. But in a permanent marker. So instead of saying, so we usually lose a lot of them in DC. So here's power supplies on the trainer. These are actually the power supplies. So this is the transformer. It's a multi-caps secondary on the transformer. Here's the rectifier. Here's the filter. Here's the filter. 7812. That's a 12-volt regulator. 79 is a minus 12-volt regulator. There's a little LEDs that come on when you turn your power supply on, right? Here's the 5-volt regulator. It's a big one. It's like a 5-amp regulator. See, there it is right there. There's the what? There's the rectifier. There's the filter, and there's the regulator right there. This is the one that goes out most often right here. Here's the variable ones right here. So these are the two variables. So this is the pot that you're turning, or the pot wired as a rheostat. This is what you're turning to tell these guys what to let pass through. So y'all know what we're talking about, the two little knobs up there? So this is the power supplies on the trainer. This is the transformer. They put a 6.3 volt transformer out and we use it solid state when we build our own power supplies. So if you take solid state, if you're in the ILT program, solid state is one of your required classes. You'll learn how to build a power supply. Pass this up. This is the maintenance form. Now we're still going to do a lab form because that's your grade. So when we deal with maintenance, we're going to be working in teams. And like I said, we're short one, so we'll be